Somewhere in the universe, a beam of energy is cutting through a galaxy right now, launched by an object so dark that not even light itself can escape it. And yet somehow, from the edge of that darkness, comes one of the brightest, most violent forces nature has ever created. A beam powerful enough to stretch for millions of light years, a flash so intense it can briefly outshine entire galaxies. A signal born from dying stars, spinning black holes, and cosmic engines that seem to bend reality itself. But what exactly are these colossal beams? How can something invisible unleash so much power? And what would happen if one ever crossed paths with a world like ours? If stories of deep space help make the night feel a little bigger, a little calmer? Consider supporting calm space science with a like, subscribe, or share. It truly helps these long-form journeys continue. And thank you for spending part of your time here. What time is it where you are, and from which corner of the world are you listening tonight? Leave a comment below. Now, let us drift into the most powerful beams in the universe. Across the universe, power does not always announce itself as an explosion. Sometimes it appears as a thin line of light, a narrow wound across the darkness, stretching far beyond the galaxy that gave it birth. It can be brighter than billions of stars and yet come from a region smaller than a solar system. It can begin near a black hole, where gravity is so strong that light itself loses the contest, and still escape as a beam of charged particles racing almost as fast as light can move. These are among the most powerful beams known in nature: relativistic jets, gamma-ray bursts, quasar outflows, and the fierce radiation launched by the most extreme engines in the cosmos. They are not beams in the simple earthly sense. They are not neat rays from a lamp or narrow columns from a searchlight. They are rivers of plasma, radiation, magnetic force, and violent motion, shaped by gravity and magnetism into structures so large that a galaxy can seem small beside them. Some last only seconds. Some continue for millions of years. Some mark the final breath of a dying star. Others are sustained by black holes so massive that they sit at the centers of galaxies like dark anchors around which entire stellar cities turn. To understand them is to follow the universe into its harshest laboratories, where matter falls, space bends, magnetic fields twist, and energy finds a way out. The first idea to settle is simple but strange. A black hole itself does not shine. It is not a furnace, not a star, not a surface burning in the dark. It is a region where gravity has curved space so deeply that anything passing too close cannot return. Yet many of the brightest objects ever observed are powered by black holes. The light comes from the material around them. Gas, dust, and broken stars spiral inward, unable to fall straight down because they carry angular momentum, the tendency to keep circling. As this material crowds into a flattened disk, it heats, collides, compresses, and glows. The energy is not created from nothing. It is released from gravity. Matter falling into a deep gravitational well gives up energy as it descends. And around a black hole the well is so deep that this release can be astonishingly efficient. A star like the Sun shines because nuclear fusion converts a small fraction of mass into energy. An accreting black hole can, under the right conditions, release a far larger fraction of the energy available from falling matter. This is one reason quasars can outshine entire galaxies. A galaxy may hold hundreds of billions of stars, but a feeding supermassive black hole can make its central region blaze brighter than all of them combined. The paradox is quiet and profound. The darkest object in physics can power the strongest light in the observable universe. Yet brightness alone is not the whole mystery. The most extreme systems do not radiate evenly in every direction. They form beams. Near the black hole, the accretion disk is not calm. It is a storm of charged particles, and charged particles create magnetic fields as they move. These fields can become wrapped, twisted, and strengthened by the disk's rotation. In the innermost region, where the gas orbits at enormous speeds and space-time itself may be dragged by the spin of the black hole, magnetic field lines can act like channels. They do not behave like solid tubes, but they guide plasma and energy into narrow directions above and below the disk. Most of the matter keeps falling inward. Some of it is redirected. A small fraction escapes along the poles, accelerated until it becomes a jet. This jet can drill out through the surrounding galaxy, cross clouds of gas, burst into intergalactic space, and end in vast glowing lobes where the particles finally slow and deposit their energy. The beam may be narrow at its origin, but its influence can spread across distances of hundreds of thousands or even millions of light years. The scale is hard to hold in thought. A black hole's immediate engine may be smaller than the region between the Sun and the outer planets, yet the beam it launches can become larger than the galaxy around it. It is as if a single hidden point in a city could produce a river of fire reaching beyond a continent. In the deep universe, this is not fantasy. Radio telescopes have revealed galaxies with twin jets extending in opposite directions, thin bright spines ending in enormous clouds of radio emission. Optical telescopes have seen jets like pale spears crossing the glow of their host galaxies. X-ray observatories have traced high-energy knots along their paths. Gamma-ray telescopes have caught even more violent flashes, some so distant that their light began travelling when the universe was young. These beams matter because they are not only displays of power, they are agents of change. A jet from an active galactic nucleus can heat the gas around a galaxy cluster, preventing that gas from cooling too quickly into new stars. It can push matter out of a galactic core, slowing the growth of the galaxy that feeds it. It can carry heavy elements, forged in stars and supernovae, into wider space. In this way, the beam is both destructive and regulating. It empties, heats, and disturbs. It also helps shape the rhythm by which galaxies evolve. The universe is not merely filled with objects sitting in silence. It is filled with feedback, where black holes influence galaxies, galaxies feed black holes, and energy flows back out into the cosmic web. The strongest beams are part of that exchange. They are how the smallest central regions can speak across the larger structures. There is another class of beam that is briefer, sharper, and in some ways more frightening. Gamma-ray bursts are flashes of high-energy radiation, often linked to the collapse of massive stars or the merger of compact remnants such as neutron stars. A gamma-ray burst does not last like a quasar. It may appear and fade in less time than a person takes to draw a breath, or it may burn for minutes before leaving a longer afterglow. Yet during that short interval, it can release as much energy as the sun will produce over its entire life, concentrated into narrow jets. The beam is deadly not because it fills all space, but because it is aimed. Most such bursts are harmlessly distant, their radiation weakened by the immense gulf between galaxies. But they show what focused cosmic violence can become. When a massive star collapses into a black hole and its outer layers erupt, jets may punch through the dying star and emerge as gamma rays. The star ends, but for a moment its collapse creates a signal visible across the observable universe. In one case, the beam is sustained by a black hole feeding at the centre of a galaxy. In another, it is born from the final collapse of a star. Different engines, different timescales. Same underlying lesson: the universe is especially dangerous when energy is focused. Human intuition often imagines power as something spread outward in a sphere, like a blast wave from an explosion. In space, some of the greatest power comes when energy is confined into a direction. A beam does not need to illuminate everything, it only needs a path. Along that path, the intensity becomes immense. This is why blazars appear so extreme. A blazar is an active galactic nucleus whose jet points almost directly toward Earth. The object is not necessarily more powerful than every other quasar, but its beam is aligned with the line of sight. Relativistic effects then amplify its brightness, compress its timescales, and make it flare with startling violence. The same engine, seen from another angle, might look less overwhelming. Perspective becomes part of the physics. The universe changes its face depending on where the observer stands. A beam pointed away is a distant structure. A beam pointed almost directly toward Earth becomes one of the brightest high-energy sources in the sky. This brings the mystery closer, though not in distance. The Milky Way has a supermassive black hole at its center, Sagittarius, a star. It is quiet now, feeding weakly compared with the great quasars of the early universe. Yet quiet is not the same as dead. Around it, stars orbit in tight paths, gas drifts, magnetic fields shift, and faint flares come and go. Evidence around the galaxy suggests that the center has been more active in the past. Above and below the plane of the Milky Way, vast bubbles of high-energy emission rise like ancient scars, hinting that something near the galactic core once released far more energy than it does today. The monster nearby sleeps lightly compared with the engines that blaze across cosmic history. It does not now send a quasar jet through the galaxy. It does not dominate the sky. But its presence shows that the same physics is not confined to remote objects with strange names. The machinery exists here too, at the heart of the home galaxy, mostly silent for the moment. The most powerful beams in the universe therefore form a connected story. They begin with gravity, but they require motion. They depend on magnetic fields, but they reveal themselves through light. They are born near darkness, yet they illuminate the distant cosmos. They can mark the death of stars, the feeding of black holes, the growth of galaxies, and the heating of space between galaxies. They carry a tension that runs through modern astronomy. The universe is creative because it is violent, and its violence is often structured, not chaotic. The beam is a shape imposed on fury. It is energy given direction. It is a sign that even near the edge of physical understanding, nature does not merely explode. It organizes, it channels, it draws thin, luminous paths through the dark. And along those paths the hidden engines of the cosmos reveal themselves. The universe first revealed its strongest beams by accident. No grand theory predicted them. No astronomer pointed a telescope toward the sky, expecting to uncover engines capable of overpowering galaxies. Instead, the discovery began as interference, as noise hidden in static, a problem that had to be solved. In the early years of radio communication, engineers sought clarity. Signals crossing long distances were disrupted by strange bursts and whispers, invisible disturbances contaminating the promise of global radio networks. Somewhere inside the hiss and crackle was a source no one understood. During the early 20th century, astronomers mostly explored the heavens through visible light. The familiar night sky seemed stable and understandable. Stars burned, nebulae glowed, galaxies drifted. The universe appeared immense, but calm. Even the expanding cosmos, slowly accepted after observations showed distant galaxies rushing away from one another, did not yet suggest violence on a cosmic scale. The expectation remained that most of the heavens were quiet places. Whatever mysteries existed were assumed to be subtle. Then came radio astronomy. In the 1930s, engineer and radio astronomer Karl Jansky began investigating unexplained interference affecting transatlantic communication systems. He built an unusual rotating antenna, large and awkward, designed not to observe planets or stars but to track sources of radio noise. Some of the interference came from thunderstorms nearby, some arrived from storms farther away, but one signal refused explanation. It repeated with remarkable consistency, not following the daily rhythm of Earth's rotation beneath the sun, but instead matching the motion of the stars overhead. Again and again, the source pointed toward the constellation Sagittarius, toward the dense heart of the Milky Way. At first, the finding seemed little more than an oddity. The sky itself was speaking in radio waves, yet no visible object explained the signal. The center of the galaxy, hidden behind thick curtains of dust, remained mysterious. Visible light could not penetrate the obscuring clouds, leaving astronomers almost blind to whatever lay there. Radio waves, however, moved through dust with far less difficulty. The invisible became faintly visible in a different kind of light. A new window had opened. Over the following decades, radio telescopes improved. They grew larger, more sensitive, and more ambitious. Instead of listening only to familiar objects such as the sun or nearby planets, astronomers surveyed the sky broadly, mapping strange radio sources scattered across the heavens. Some matched visible galaxies. Others seemed to emerge from empty darkness. They appeared as tiny pinpoints, too compact to resemble known nebulae, too intense to dismiss as measurement error. Their positions offered few clues. Some sat near the plane of the Milky Way, while others floated far above or below it. Because the galaxy forms a flattened disk, astronomers faced a difficult choice. Either these radio sources were relatively close, hidden somehow within the neighborhood of stars, or they were impossibly distant, scattered among faraway galaxies. Neither possibility made sense. If nearby, they should have visible counterparts. If distant, they implied absurd levels of energy. The strongest among them would need to outshine entire galaxies simply to appear so bright across such vast distances. Many astronomers resisted this conclusion. The universe already felt large enough. To suggest the existence of compact engines brighter than hundreds of billions of stars sounded unreasonable, even embarrassing. There had to be another explanation. Perhaps the measurements were flawed. Perhaps the radio sources were unusual stars closer to home. Perhaps something in physics had been misunderstood. The strange points were catalogued cautiously under a technical name, quasi-stellar radio sources. The term reflected uncertainty. They looked almost like stars in telescopes, yet behaved unlike anything familiar. The phrase was clumsy, eventually shortened into something sharper, stranger, and destined to become famous quasar. Yet the name solved nothing. It merely acknowledged the puzzle. The breakthrough came when astronomers found a way to match radio signals with visible light. In the early 1960s, radio techniques improved enough to measure the sky with much greater precision. One object, catalogued as 3C273, passed behind the Moon in a predictable event called an occultation. By carefully measuring the timing of its disappearance and reappearance, astronomers pinned down its exact location. There, in visible light, sat a faint star-like object. At first glance it seemed unremarkable, but when astronomers studied its spectrum, everything changed. Every element leaves fingerprints in light. Dark and bright lines spread across specific wavelengths. Hydrogen, helium, oxygen, and carbon each mark radiation in recognizable patterns. The spectrum of 3C273 contained these familiar signatures, but shifted far toward the red end of the spectrum. The object was receding at extraordinary speed, or rather, space itself between the object and Earth had stretched enormously. The conclusion carried profound consequences. 3C273 was billions of light-years away. The light arriving at Earth had begun its journey long before complex life existed on this planet. Yet despite the distance, it remained astonishingly bright. No ordinary star could explain it. No known stellar process approached the necessary energy. The universe had revealed something new. Worse still, the object flickered. Its brightness changed noticeably over short periods. This mattered because changes in brightness reveal size. A large object cannot vary instantly. Light itself takes time to cross distance. A galaxy spanning thousands of light-years cannot brighten and dim in months. The region responsible had to be compact, perhaps no larger than the solar system itself. Somehow, an area smaller than the space around the Sun was producing more energy than an entire galaxy of stars. The implications unsettled astronomy. Here stood an object brighter than imagination allowed, smaller than theory preferred, and farther than many believed possible. Gradually, more quasars emerged. Dozens became hundreds. Their properties varied. Some glowed fiercely in radio wavelengths. Others emitted intense X-rays. Some appeared calm. Others flared violently. Yet a pattern slowly emerged. Many lived at the centers of galaxies. Their host galaxies sometimes appeared distorted, interacting, or merging with neighbors. Something important seemed to happen in galactic cores. By then, astronomers had also begun uncovering another strange possibility. Black holes, once dismissed as mathematical oddities hiding in Einstein's equations, were becoming physically plausible. Theoretical work suggested that massive stars could collapse beyond any stable state, crushed by gravity into regions from which light itself could not escape. Evidence accumulated slowly. Then systems like Cygnus X1 revealed compact invisible companions devouring nearby stars and emitting fierce X-rays. Black holes existed. Once accepted, the idea spread rapidly. If stellar black holes could feed on nearby matter and shine brightly through the process of accretion, perhaps quasars represented the same mechanism on a much grander scale. Instead of black holes several times heavier than the Sun, what if galaxies contained monsters weighing millions or billions of solar masses? What if the brightest objects in the cosmos were powered not by fusion, but by gravity itself? The suggestion transformed astronomy. It explained the compactness of quasars. It explained their brightness. It explained their location in galactic centers. Most importantly, it hinted at the origins of the powerful beams soon to be uncovered. Radio observations had already revealed bizarre structures around some galaxies. Long streams extended outward for astonishing distances, ending in glowing lobes larger than galaxies themselves. The galaxy Cygnus A became one of the clearest examples. At its center sat an unusually bright nucleus. Stretching outward were immense twin jets of radio emission, narrow and disciplined despite spanning hundreds of thousands of light-years. Whatever powered them lay hidden in the galactic core. The beam had become impossible to ignore. It was not merely brightness anymore. The universe seemed to be launching matter itself across unimaginable distances. Charged particles raced outward at near-light speed, guided somehow into coherent streams. The radio sky no longer looked quiet. It looked violent, organized, and strangely mechanical. The old image of galaxies as serene islands of stars began to collapse. Instead, some galaxies resembled engines. At their centers sat compact sources consuming matter and releasing energy in startlingly focused ways. Astronomers coined a broader term: active galactic nuclei. Quasars, radio galaxies, blazars, and other bizarre cosmic objects increasingly appeared to be related, different expressions of the same underlying machine viewed from different distances and angles. The realization carried a deeper implication. the strongest beams in the universe were not rare accidents. They emerged naturally wherever conditions allowed gravity, motion, and magnetism to cooperate. A black hole alone remained dark, but feed it enough matter, surround it with chaos, spin it fast enough, and the darkness became an engine. The beam emerged not despite gravity, but because of it. The same force that traps light could also create the brightest structures ever seen. By the end of the 20th century, astronomy had changed permanently. The universe no longer looked calm, it no longer seemed orderly in the old sense. Beneath the stars, hidden inside galaxies, lurked engines capable of rearranging matter across intergalactic scales. What began as interference in a radio antenna had become a revelation the cosmos was threaded with invisible beams, and somewhere deep in the darkness, giant forces were already at work. A black hole begins not as darkness, but as the last answer to a star that can no longer hold itself together. For most of its life, a star survives by balance. Gravity pulls inward, trying to compress the star toward its center, while heat and radiation from nuclear fusion push outward. This balance can last for millions, billions, or even trillions of years, depending on the star's mass. Massive stars live more fiercely. Their cores are hotter, their pressure is greater, and their fuel disappears quickly. They shine with extraordinary brightness, but that brilliance is a form of spending. The more massive the star, the faster it burns through the material that keeps gravity at bay. In the end, the struggle becomes unequal. Hydrogen gives way to helium, helium gives way to heavier elements, and the star's core builds layer after layer of nuclear ash. Carbon, oxygen, neon, silicon, and other elements form in sequence, each stage shorter and more intense than the last. At the deepest center, iron eventually appears. Iron is different. Fusion of iron does not release useful energy in the way earlier reactions do. It consumes energy. The engine that held the star up begins to fail. The core loses support. Gravity, patient through the star's entire life, finally wins. Collapse begins. In a massive star, that collapse can happen with terrible speed. The core contracts, densities rise, particles are forced into states unlike ordinary matter, and the outer layers of the star fall inward. If the remaining core is not too massive, collapse may halt in a neutron star, an object so dense that atoms themselves have been crushed into a compact sphere of nuclear matter. But if the collapsing core is heavier still, no known pressure can stop it. Not heat, not atomic structure, not the resistance of packed neutrons. The core continues inward past every stable form. Space curves more sharply, the escape speed climbs. At a critical boundary, the escape speed becomes greater than the speed of light. An event horizon forms. From that moment, the object is a black hole. The phrase sounds simple, but it hides a radical change in reality. The event horizon is not a surface made of material. It is a boundary in space-time, a point of no return. Outside it, light can still escape if aimed correctly. Inside it, all future paths lead inward. The black hole may be born from a star, but it is no longer a star. It has no glowing surface, no layers of gas, no furnace of fusion. To the outside universe, it can be described by mass and spin. It is both astonishingly simple and almost impossible to visualize. The matter that once formed a stellar core has disappeared behind a boundary where ordinary intuition fails. Yet the black hole's gravity remains. A star can die, vanish from view, and still leave behind a gravitational presence strong enough to reshape everything around it. Stellar black holes are only the beginning. They may weigh several times the mass of the Sun, or several tens of solar masses, depending on the star that formed them and how much mass was lost before collapse. But the most powerful beams in the universe require a far greater scale. They require black holes not of tens of solar masses, but of millions, billions, and perhaps tens of billions. These supermassive black holes are the dark engines in galactic centers. Their origin remains one of the great open questions in astrophysics. They may begin as the remnants of the first massive stars, forming in the early universe when gas contained almost no heavy elements and stars could grow unusually large. They may also form through the direct collapse of enormous primordial gas clouds, bypassing the ordinary star stage and creating heavy seeds from the start. Once formed, they grow by feeding on gas, swallowing stars, and merging with other black holes as galaxies collide and combine. Over cosmic time, small seeds can become immense. But some quasars appear so early in cosmic history, powered by black holes already weighing billions of solar masses, that growth alone becomes difficult to explain unless the seeds were large, the feeding was rapid, or the early universe supplied unusually favourable conditions. This is where black holes become more than endings. They become architects. In the dense young universe, matter gathers into filaments, halos, and forming galaxies. Gas falls inward. Stars ignite. The first heavy elements spread through space after stellar deaths. In the crowded centers of growing galaxies, black holes sink toward the deepest gravitational wells. There, they find fuel. A quiet black hole is nearly invisible, but a fed black hole becomes surrounded by motion. Gas does not simply drop in, it swirls, flattens, collides, and heats. Stars passing too close may be pulled apart by tidal forces, stretched by uneven gravity until their material becomes a stream. Some of that gas escapes. Some remains bound. Some joins the disk around the black hole. The darkness has no surface to burn, but the region around it can blaze. This is the first step toward a cosmic beam. The second step is spin. Black holes can rotate, sometimes rapidly, especially if they form from rotating stars or grow by feeding from disks that carry angular momentum. A spinning black hole is not merely a passive pit. According to general relativity, it drags the space-time around it, creating a region outside the event horizon where space itself is pulled into rotation. This region is called the ergosphere. When magnetic fields from the accretion disk thread this region, they may tap rotational energy and help launch jets. The details are still studied with simulations, observations, and theory, but the broad picture is clear. Gravity provides the energy of falling matter. Rotation stores additional energy in the black hole and disk. Magnetic fields provide structure. Together they create conditions in which energy can be extracted and directed along the poles. The result is not an explosion in every direction. It is an axis. It is a preferred path through space. The black hole becomes an engine with two outlets, one above the disk and one below it. The jets that emerge do not come from inside the event horizon, because nothing returns from there. They arise from the furious environment just outside it, from plasma and magnetic fields shaped by the black hole's gravity and spin. This distinction matters. The black hole itself remains dark, but its surroundings become one of the most efficient energy machines in nature. Matter falls inward and gives up energy. Magnetic fields twist and guide charged particles. Radiation floods outward. A small fraction of material escapes in focused streams moving close to light speed. The birth of the dark engine also changes the galaxy around it. A supermassive black hole may contain only a small fraction of a galaxy's total mass, yet its influence is concentrated at the center, where gas is most available and where star formation can be altered. When the black hole feeds strongly, radiation and jets push back into the surrounding medium. They heat gas that might otherwise cool into stars. They excavate cavities and clusters of hot plasma. They blow material away from galactic cores. This feedback prevents galaxies from growing without limit and helps explain why the largest galaxies are not simply packed with endless new stars. In a strange way, the black hole's violence can regulate creation. By disturbing gas, it slows birth. By launching energy into space, it shapes the future architecture of the galaxy. The most powerful beams therefore begin with a sequence of transformations. A star collapses, a black hole forms. Black holes gather in galactic centers. Gas feeds them. Disks ignite. Magnetic fields twist. Spin lens direction. The beam escapes. The beams are visible across the universe because they are not merely local accidents. They are the outward signs of a hidden engine operating at the limit of what matter and space-time can do. In them, the universe shows how an ending becomes a source. The death of stars creates black holes. Black holes help build quasars. Quasars illuminate the early cosmos. Jets sculpt galaxies and clusters. Darkness becomes structure. Collapse becomes motion. The path from a dying star to a beam crossing intergalactic space is long, but it is continuous. It reveals a universe where the most extreme forces are connected, and where the boundary between destruction and creation is never as clean as it first appears. Around a feeding black hole, matter does not fall like a stone dropped into a well. It arrives with motion, memory, and disorder. Gas drifting through a galaxy carries the rotation of its parent cloud. Torn fragments of stars carry the paths they followed before gravity broke them apart. Dust, plasma, and magnetic fields arrive from different directions, colliding and mixing in the crowded region near the center. Because of this, matter rarely plunges straight into the event horizon. It circles, it misses, it overshoots, it spreads into orbit. Slowly, under the pressure of collisions and friction, the material settles into a flattened whirlpool called an accretion disk. This disk is one of the most important structures in high-energy astronomy. It is the place where falling becomes light. At great distances from the black hole, gas may be cold and thin, hardly different from the faint material between stars. Closer in, the story changes. Each orbit is faster than the one outside it. The inner gas races ahead while the outer gas lags behind, and the disk is sheared into layers moving at different speeds. Those layers rub, collide, and churn. Turbulence spreads through the plasma. Energy that once belonged to orbital motion becomes heat. The temperature rises. At first, the disk glows in longer wavelengths, then visible light, then ultraviolet, and in the innermost regions, X-rays. The black hole remains unseen, but the disk around it becomes a furnace without a solid surface, a moving structure so bright that it can overwhelm the light of its host galaxy. The power comes from gravity's depth. On Earth, falling releases only a small amount of energy because Earth's gravity is weak compared with the gravity near a black hole. Around a supermassive black hole, gas falls into a much deeper well. As it moves inward, it must lose energy to continue its descent. That lost energy is not erased. It becomes radiation, heat, particle motion, and magnetic stress. This is why accretion can be more efficient than fusion in turning available mass energy into light. In stars, fusion works patiently in a core, converting a small fraction of matter into radiation over immense spans of time. Around a black hole, gravity can draw energy from infalling matter with astonishing efficiency. A quasar is not powered by a black hole glowing from within. It is powered by matter being forced to surrender energy before disappearing. The disk, however, is not simply a bright ring. It is unstable, layered, and alive with forces. Because its gas is ionized, meaning stripped into charged particles, it responds strongly to magnetic fields. Electrons and ions spiral along field lines. Their motion creates new fields. Small disturbances grow. In a rotating disk, magnetic fields can act like hidden springs connecting neighboring rings of gas. The inner ring moves faster, pulls ahead, stretches the field, and transfers angular momentum outward. This process allows some gas to move inward while other gas carries away the excess rotation. Without it, much of the disk would remain trapped in orbit, circling forever and never feeding the black hole. Magnetism is therefore not decoration. It is part of the machinery that allows accretion to continue. It helps turn a crowded disk into an engine. As material approaches the innermost stable orbits, the conditions become more extreme. There is a point near a black hole where circular paths stop being safely possible. Outside this boundary, gas can orbit, at least for a time. Inside it, stable orbit gives way to plunge. The exact distance depends on the black hole's spin. Around a rapidly rotating black hole, some matter can orbit closer before being lost. This closeness matters because the deeper the gas travels before falling in, the more energy it can release. Near the edge, space is no longer a passive stage. Relativity dominates. Time runs differently compared with distant regions. Light bends sharply. Radiation from the far side of the disk can curve around the black hole and arrive from unexpected directions. The disk appears warped by gravity itself, its brightness altered by motion, its colour shifted by speed and depth. The inner disk is not a peaceful place. It is a luminous storm wrapped around an abyss. Yet even there, the flow is regulated. A black hole can only feed so fast before its own radiation pushes back. As the disk brightens, photons carry momentum outward. This radiation pressure can lift gas, drive winds, and slow the inflow. If too much matter rushes in, the disk becomes brilliant enough to resist further feeding. If the supply fades, the radiation weakens and gas can fall more easily again. In this way, an accreting black hole can behave less like a single explosion and more like a long-running engine with feedback. It flares, dims, steadies, and shifts. The balance is never perfect. Some quasars flicker. Some active galactic nuclei brighten and fade over time. The beam, if one forms, depends on this changing supply. Without fuel, the disk thins. Without the disk, magnetic fields weaken. Without strong fields and plasma, the jet cannot remain powerful. The hunger of giants is therefore not only about appetite, it is about supply. A supermassive black hole may be enormous, but it cannot shine as a quasar unless gas reaches the centre. This is why the early universe is so important. Young galaxies are gas-rich. They collide more often. Their central regions are disturbed, stirred, and replenished. Gravitational encounters can pull gas out of stable orbits and send it inward. Galaxy mergers can funnel vast reservoirs towards central black holes. Under those conditions, the disk becomes dense and luminous. The black hole feeds. The quasar awakens. In the quieter present-day universe, many galactic centres have less available fuel. Their black holes remain. But their engines idle. The monster is still there, but the banquet has ended or paused. Our own Sagittarius, a star, shows this contrast clearly. It holds millions of solar masses, yet it is faint compared with quasars because it currently receives little material. The strength of the engine depends not only on the size of the black hole, but on whether the surrounding galaxy is delivering matter to its door. When feeding becomes intense, the disk does more than shine. It produces winds. Radiation pushes on gas. Magnetic fields fling material from the disk surface. These outflows can be wide and heavy, unlike the narrow relativistic jets that rise from the poles. Disk winds may carry enormous amounts of mass back into the galaxy, enriching and disturbing the surrounding environment. They can block light from some directions, making the same object appear different depending on viewing angle. From one line of sight, the central disk may be visible as a brilliant quasar. From another, dust and gas may hide the core, leaving only infrared glow or radio structure. The active galaxy becomes a changing shape, not because the engine is fundamentally different, but because its geometry matters. Around the hidden center, orientation becomes fate. The beam is the most dramatic sign, but it is only one part of the black hole's influence. The disk, winds, radiation, and surrounding dust form a connected system. A thick torus of colder material may encircle the central region, feeding and obscuring it. Hot clouds move above the disk, producing broad spectral lines as they race through the black hole's gravity. Farther out, narrower emission regions glow under the quasar's radiation. Every layer records a different distance from the engine, a different temperature, a different speed. The black hole's hunger writes itself into light. Astronomers decode that light to estimate mass, motion, chemistry, and distance. A quasar is too far away to see in ordinary detail, but its spectrum becomes a map of its hidden structure. The most powerful beams begin here, in this crowded transition between order and collapse. The disk must feed the black hole, but not all material is swallowed. Some is heated and thrown outward, some is lifted into winds, some is caught by magnetic fields and accelerated into jets. The beam is not separate from the hunger, it is a consequence of it. The same matter that tries to fall helps build the conditions that allow some energy to escape. The same gravity that traps light drives the disk to shine. The same darkness that seems like an end becomes a source of motion, radiation, and structure. In the heart of a galaxy, the giant feeds, and the universe answers with light sharp enough to cross cosmic time. A beam from a black hole is not a simple spray of fire. It is a structure, narrow at its birth and immense in its reach, shaped by forces that are invisible until matter begins to obey them. Near the center of an active galaxy, the accretion disk turns with furious speed. The inner regions race around the black hole faster than the outer regions, and the charged gas inside the disk produces magnetic fields that twist with the motion. Over time, these fields become wound into powerful shapes, like tension stored in an invisible spring. Plasma caught in this magnetic architecture can be lifted away from the disk and guided along the black hole's rotation axis. The result is a pair of jets, one launched above the disk and one below it, moving in opposite directions into space. They do not emerge from inside the event horizon. Nothing does. They rise from the intense region just outside it, where falling matter, rotation, magnetism, and curved space-time meet at the base. The jet may be only a tiny fraction of a galaxy's size. Farther out, it becomes one of the largest coherent structures in the universe. This is the first strange fact about cosmic beams. They begin in a place where everything seems crowded, hot, and chaotic. Yet they escape as long, focused streams. Chaos does not prevent order. Under the right conditions, it creates it. The charged particles inside these jets move at relativistic speeds, meaning speeds close enough to the speed of light that ordinary intuition fails. Time, brightness, and direction become distorted by motion. When a jet points nearly toward Earth, its light appears amplified and its changes seem compressed. This source can brighten violently, not always because the engine has changed dramatically, but because the beam is aimed almost directly along the line of sight. This is the nature of a blazar, one of the most extreme forms of active galactic nucleus. It is not necessarily a different creature from a quasar or radio galaxy. It may be the same kind of engine seen from a more dangerous angle. The universe often hides unity beneath perspective. From the side, a jet may appear as a long radio structure extending from a galaxy. From nearly head-on, it becomes a flashing beacon of gamma rays and high-energy light. The same beam becomes mild or overwhelming depending on alignment. In this way, cosmic jets make astronomy partly geometric. What is seen depends on where the observer stands relative to the engine's axis. The jet does not move through empty nothingness. Even intergalactic space contains thin gas, magnetic fields, photons, and particles. As the beam travels outward, it interacts with this environment. It may remain narrow for astonishing distances, held together by magnetic fields and its own forward momentum. It may wobble, bend, or break into knots where faster material catches slower material, or where pressure changes along the path. Each knot can glow brightly, revealing shocks inside the flow. Particles are accelerated again and again, spiraling around magnetic fields and producing radio waves through a process known as synchrotron emission. The name is technical, but the idea is clear charged particles forced into curved paths by magnetic fields radiate energy. In cosmic jets, this radiation can reveal streams that would otherwise be invisible. The beam writes its path across the sky in radio light, X-rays, and sometimes visible glow, allowing astronomers to trace a structure far too thin, distant, and faint for ordinary sight. The galaxy M87 offers one of the most famous examples. At its centre lies a supermassive black hole weighing billions of solar masses. From the region around it, a bright jet extends thousands of light-years into space. Visible as a slender feature cutting across the galaxy's glow, the jet was noticed long before the black hole itself could be imaged, a sign that the engine was announcing itself through its outflow. Later, the Event Horizon Telescope revealed the shadow of the black hole in M87, a dark centre ringed by light from hot plasma. The image did not show the full jet in dramatic detail, but it helped anchor the story. The distant beam and the near horizon belong to the same system. The narrow structure spanning thousands of light-years begins near a boundary where light can barely escape. M87 becomes a bridge between scales: the event horizon, the accretion flow, the launching region, the visible jet, and the wider galaxy all belong to one connected machine. Far beyond galaxies like M87, radio jets can grow even larger. Some active galaxies launch twin beams that cross hundreds of thousands or millions of light-years before ending in enormous lobes. These lobes form where the jets slow down, collide with surrounding gas, and inflate bubbles of energetic particles. To radio telescopes, the result can look like a central galaxy with two vast glowing wings. The galaxy itself may be only the seed of the structure. The lobes can reach far beyond its stars, spreading into the space between galaxies. They are not decorative remnants. They carry energy into the wider environment, in galaxy clusters, where many galaxies sit inside huge atmospheres of hot plasma. Jets from central black holes can carve cavities, stir gas, and prevent it from cooling too quickly. Without this heating, gas in cluster cores might condense rapidly, producing far more star formation than is observed. The beams act like cosmic regulators. They do violence, but that violence creates balance. They disturb the gas enough to slow collapse. They keep the largest structures from cooling into something different. The beam that begins near a black hole becomes a thermostat for an entire cluster. This feedback is one of the deepest reasons jets matter. They show that black holes, despite being compact compared with their host galaxies, can influence enormous volumes of space. A supermassive black hole may contain only a small fraction of a galaxy's total mass, but when it feeds, it releases energy from a region of exceptional intensity. That energy is not locked near the center. Jets carry it outward efficiently. Instead of heating only the immediate neighborhood, they deliver power to the outskirts, to halos, to cluster gas, and to the intergalactic medium. This means black holes help govern the growth of galaxies. They can slow star formation by heating or removing gas. They can spread heavy elements created by earlier generations of stars. They can reshape magnetic fields across vast distances. The beam is a messenger from the central engine, but it is also a tool. It changes the place it passes through. It leaves behind cavities, shocks, filaments, and radio lobes, fossil evidence of episodes that may have ended long ago. Some galaxies carry these relics like memories of former activity. Their central black holes may now be quiet, but the surrounding space still glows with the history of past jets. There is a quiet irony in their shape. An explosion normally spreads. A jet narrows. The strongest beams in the universe are powerful not only because of the total energy they carry, but because that energy is organized. Focus turns power into reach. A broad wind may batter a galactic center, but a jet can drill through it. The beam follows the path of least resistance along the rotation axis, piercing the surrounding material and escaping into larger space. It may remain coherent because it moves so fast, because magnetic fields confine it, and because the surrounding medium cannot easily disrupt it. Yet even a jet is not perfectly steady. It pulses with changes in the feeding disk. It flickers as magnetic fields reconnect. It may turn if the black hole's spin axis changes after mergers, or if the disk becomes misaligned. Some radio galaxies show bent or restarted jets, suggesting that engines can switch off and on, or change direction over time. A beam across the sky may therefore be a record of motion through deep time, not a single unchanging spear. The full life of a jet can outlast human civilization many times over. Material launched from the center travels outward for thousands or millions of years. By the time it reaches the outer lobes, the engine that launched it may already have changed. Astronomy sees these structures as whole shapes, but they are also timelines. The inner jet shows the recent activity of the black hole. The outer lobes preserve older outbursts. The gaps, bends, and knots reveal interruptions, shocks, or renewed feeding. A single radio image can contain the history of a galactic core written across distances larger than the Milky Way. In that sense, beams are not just violent features. They are archives. They record how a black hole has eaten, rested, awakened, and pushed back against its surroundings. The most powerful beams that pierce galaxies are therefore not accidents of brightness. They are the visible consequences of a hidden order. Gravity pulls matter inward. Rotation prevents a direct fall. Friction and turbulence make the disk shine. Magnetic fields draw energy into structured paths. Plasma escapes along the poles. The jet crosses the galaxy, enters intergalactic space, and ends as a vast glowing wound in the cosmic environment. From darkness comes direction. From collapse comes a beam. From a point near the edge of no return comes a structure large enough to reshape the fate of galaxies. Quasars are lighthouses built around darkness. They appear across the universe as brilliant points, often so far away that their host galaxies are difficult to see. Yet their light travels for billions of years and still reaches telescopes on Earth. At first, this seems almost contradictory. A quasar is powered by a black hole, an object defined by the absence of escaping light. But the quasar itself is not the black hole. It is the storm around it, the accretion disk, the hot plasma, the magnetic fields, the winds, and sometimes the narrow jets that burst from the centre with extraordinary force. In the young universe, these storms were common. Galaxies were closer together, richer in gas, and more frequently disturbed by mergers. Their centres received fuel more easily. Supermassive black holes that might later grow quiet were then surrounded by thick inflows of matter. When those inflows became intense, the galactic nucleus awakened. The central region could shine brighter than every star in the galaxy combined. From across cosmic distance, the galaxy itself faded into a faint surrounding glow, while the quasar burned like a single impossible star. The word quasar comes from their early appearance as quasi-stellar objects, star-like points that were not stars at all. Their spectra revealed the truth. The lines of familiar elements were shifted far toward longer wavelengths, showing that the light had been stretched by the expansion of space. These objects were not nearby oddities. They were remote beacons from a younger cosmos. Their brightness became a problem that demanded a new kind of engine. Only accretion onto supermassive black holes could explain how so much energy could emerge from such compact regions for such long periods. A quasar may vary in brightness, meaning the source of its light cannot be spread across a whole galaxy. The central engine must be small compared with the galaxy it outshines. This compactness is part of what makes quasars so strange. A region on the scale of a solar system or somewhat larger can dominate the light of a galaxy spanning tens or hundreds of thousands of light years. The small centre overwhelms the vast whole. The early universe is the natural home of quasars because youth means fuel. Galaxies are still assembling. Streams of cold gas flow along the cosmic web. Collisions and close encounters disturb orderly rotation and send material inward. The black hole at the centre does not need to chase its meal. Gravity and galactic structure deliver it. As gas spirals in, the disk brightens. Radiation pushes outward. Winds rise from the disk. If the magnetic conditions and spin are right, jets form along the poles. The quasar becomes not only a bright object, but a system of exchange. Matter falls inward, energy escapes outward, and the surrounding galaxy is transformed. In some cases, quasar winds may remove gas that would otherwise form stars. In others, pressure from jets may compress distant clouds and help trigger star formation along their edges. The relationship is not simple destruction. It is regulation, disturbance, and renewal. A quasar can both starve and sculpt its host. This is why quasars are among the most important tools for studying the early cosmos. Their light is bright enough to act as a background lamp, shining through the material between galaxies. As that light passes through clouds of hydrogen and traces of heavier elements, some wavelengths are absorbed. By studying these missing pieces in the quasar spectrum, astronomers infer the chemistry, temperature, and distribution of intergalactic gas across cosmic time. A quasar is therefore both engine and probe. It reveals the black hole that powers it, but also illuminates the universe through which its light travels. The farther the quasar, the older the message. Its photons may have left when the first generations of galaxies were still growing, long before the Sun existed, long before Earth had condensed from the debris of earlier stars. Looking at a distant quasar is not simply looking across space. It is looking into an era when galaxies were younger, gas was more abundant, and black holes were building themselves with unsettling speed. Some of the most distant quasars deepen the mystery. They are seen when the universe is less than 1 billion years old. Yet they already contain black holes with masses of hundreds of millions or even billions of suns. This creates a timing problem. A black hole can grow by accreting matter, but radiation from that accretion pushes back against the inflow. If it feeds too quickly, its own light can drive material away. There is a natural limit to steady growth, often described through the balance between gravity pulling gas inward and radiation pressure pushing it outward. For the earliest giant quasars to exist, their black hole seeds must either have formed unusually massive, fed with exceptional efficiency, grown through mergers, or experienced episodes that pushed beyond simple assumptions. Each possibility points to a young universe more fertile and violent than the calm night sky suggests. Quasars are not only bright, they are clues that cosmic structure matured rapidly. The beams from quasars make them even more formidable. Not every quasar produces a powerful radio jet, but when it does, the jet can carry energy far from the nucleus. In radio, loud quasars. The central engine launches particles that travel close to light speed, producing radio emission along the jet and in lobes at its ends. When the jet points near the line of sight, the quasar may appear as a blazar, flaring strongly in gamma rays and changing brightness on short timescales. Relativistic motion compresses the signal. A small shift in the jet can produce a large change in observed brightness. The object seems restless, sometimes violently so. Yet behind the apparent flicker lies the same broad structure, a black hole, a disk, magnetic fields, and a beam. The quasar's identity depends partly on angle, partly on power, and partly on how much dust blocks the view. One cosmic engine can wear many faces. The most luminous quasars sit near the edge of comprehension because they combine duration with intensity. A supernova can briefly rival a galaxy. A gamma-ray burst can outshine almost everything for moments, but a quasar can remain active for millions of years, sustained by a continuing supply of matter. Over such spans, the total energy released becomes enormous. The beam, if present, turns that energy into a focused influence stretching beyond the host galaxy. It can heat intergalactic gas, inflate radio lobes, and leave fossil structures long after the quasar itself fades. The active phase is temporary, but its effects persist. A galaxy that once hosted a quasar may later look quiet, its central black hole dim, its stars aging normally. Only extended radio relics, disturbed gas, or large-scale bubbles may reveal the older violence. In this way, quasars are episodes in galactic life rather than permanent identities. They are awakenings. Some galaxies are caught during their blaze, others are seen before or after. There is a deep calm in realizing that the brightest beacons in the universe are temporary. Even the strongest engines depend on circumstance. They need gas, mergers, instability, and time. When the fuel supply drops, the disk thins, the radiation fades, the jet weakens. The quasar becomes an ordinary active nucleus, then perhaps a quiet galactic center. The black hole remains, but its voice becomes faint. The universe seen nearby is filled with such quiet monsters. Their youth has passed, or their next feeding has not yet begun. In the distant universe, however, quasars mark a time when many of these monsters were awake at once, blazing through cosmic dawn and afternoon. Their light now reaches Earth as an archive of that lost activity. Each quasar is both ancient and present ancient because the event occurred billions of years ago, present because the photons arrive now and enter the instruments that measure them. The lighthouse shines across time, not because the engine still burns in the same way, but because space has preserved the journey of its light. Quasars show that the universe is not evenly powerful. It concentrates energy into centers, into disks, into beams, into rare alignments. It creates objects that can be mistaken for stars and then revealed as the hearts of galaxies. It hides black holes inside radiance and uses darkness to illuminate the earliest chapters of cosmic history. The beams of quasars are therefore more than violent streams. They are signatures of a universe learning to build structure, regulate galaxies, and scatter energy across scales almost too large to describe. They rise from places where gravity nearly closes all paths, yet one path remains open along the poles. Through that path the deep engine speaks. Its message crosses billions of light years, softened by distance but not erased, telling of a time when the centres of young galaxies burned with the strongest light nature has learned to make. TON 618 sits near the edge of scale, not because it is the only giant in the universe, but because it gathers several extremes into one distant source. It is a quasar, a blazing galactic nucleus powered by a supermassive black hole feeding on matter in the young cosmos. To Earth, it is not a visible monster in the ordinary sense. It is a point of ancient light, faint in the sky, its host galaxy swallowed by distance and glare. Yet that faint point represents a central engine whose mass may reach tens of billions of suns. Around it, an accretion disk shines with the energy of matter, falling into one of the deepest gravitational wells known. TON 618 is not important simply because it is large. It is important because its scale asks how the universe builds such giants at all, how feeding can continue so efficiently, and how a compact dark object can influence regions far beyond itself. The first difficulty is distance. The light from TON 618 has crossed so much expanding space that it shows the universe as it was long ago. In that earlier era, galaxies are still growing rapidly, rich in gas and often disturbed by interactions. The quasar's glow acts like a signal from a time when supermassive black holes were assembling with great speed. The black hole at its centre is not seen directly. Its mass is inferred from the motion and brightness of the gas around it, from broad emission lines in its spectrum and the luminosity of the quasar. These methods carry uncertainty because the quasar must be read through light, motion, and models. The result is still astonishing, even allowing for uncertainty. TON 618 belongs to the realm of ultramassive black holes, objects so heavy that they make the black hole at the centre of the Milky Way seem small by comparison. A black hole of such mass has an event horizon so large that the scale of a planetary system becomes a poor measure. The boundary of no return would span a region measured not in cities, planets, or ordinary orbits, but in distances that approach the architecture of entire solar systems. Yet the event horizon itself is not the shining part. The light comes from outside, where gas is compressed, heated, and driven into violent motion. Around a black hole this large, the accretion disk can be immense, but the basic physics remains familiar. Matter spirals inward, energy is released. Radiation floods outward. Magnetic fields organize charged particles. If a jet forms, it rises along the spin axis, not from inside the black hole, but from the region where plasma and magnetism couple to the rotating space-time near it. The engine is larger, the reservoir greater, the brightness harder to comprehend. TON 618 therefore forces a question that reaches beyond spectacle. How does a black hole become so massive one path is gradual feeding? Gas falls in over millions and billions of years, steadily increasing the black hole's mass. Another path is merging. When galaxies collide, their central black holes may eventually sink toward one another and combine, creating a larger remnant. But these processes require time, and distant quasars show large black holes when the universe is still relatively young. This does not make them impossible, but it narrows the options. The earlier seeds may need to be heavier than simple stellar remnants. They may form from the collapse of massive gas clouds in rare environments, or from dense clusters where stars and black holes merge quickly. They may feed in bursts, sometimes approaching the limits set by radiation pressure. The young universe may offer dense flows of cold gas that deliver fuel with fewer interruptions. Ton 618 stands as a clue that the early cosmos can grow dark engines faster than once seemed comfortable. The beam, whether expressed as a narrow jet or a broader quasar outflow, becomes a sign of what such growth does to the surroundings. A black hole cannot feed without affecting its meal. Radiation from the accretion disk presses against incoming gas. Winds rise from the disk's surface and carry material outward. Magnetic fields can drive streams away from the center. If a relativistic jet is launched, it may bore through the host galaxy and reach into intergalactic space. In such a system, the black hole is not merely consuming, it is also pushing back. This pushback may limit further growth, clearing gas from the galactic core or heating it enough that star formation slows. The giant feeds. But the act of feeding makes continued feeding harder. This tension may help explain why galaxies and their central black holes seem linked across cosmic history. The black hole is tiny compared with the galaxy, yet its energy output can alter the galaxy's gas supply. Ton 618 shows this relationship in exaggerated form. An engine so powerful that its influence may have spread through its host like a central storm. Its luminosity also reveals how beams and radiation can turn distant objects into cosmic landmarks. A normal galaxy at such distance would be difficult to study in detail. A quasar announces itself. Its central brightness cuts across billions of light years, carrying information about the engine and the intervening universe. As its light travels, clouds of gas absorb parts of the spectrum, leaving faint traces of hydrogen and heavier elements across the line of sight. The quasar becomes a lamp behind the cosmic web. Its power is therefore useful as well as extreme. It helps astronomers measure matter between galaxies, study early chemical enrichment, and test how structure has changed with time. Still, the scale remains unsettling. Around a black hole of tens of billions of solar masses, time and space near the horizon behave in ways that push the imagination to its edge. Close to the event horizon, light paths curve sharply. Radiation from the disk may be bent, magnified, and redshifted. Gas can orbit at enormous speeds before crossing the point beyond which no signal returns. To a distant observer, matter nearing the horizon appears to slow and fade, its light stretched and dimmed by gravity. For the infalling material itself, the journey continues inward. The horizon is crossed without a local surface or wall, yet the path back to the wider universe is gone. Ton 618 therefore combines the largest visible radiance with the deepest invisibility. Its brilliance is a ring of consequence around a place that cannot be seen. It is tempting to call such an object impossible, but astronomy has learned caution with that word. Quasars once seemed impossible. Stellar black holes once seemed doubtful. Supermassive black holes once felt extravagant. Again and again. The universe has filled the extreme parts of theory with real objects. The existence of ultramassive black holes does not break physics, but it tests the stories built around growth, feeding, and environment. It asks whether the first black hole seeds were born large, whether early galaxies could drive gas inward efficiently, whether mergers built giants faster than expected, and whether radiation sometimes fails to halt accretion as neatly as simple models suggest. These are not signs of failure. They are signs of a frontier. Ton 618 is not merely a record holder. It is a question in light. The strongest beams in the universe become most meaningful at this frontier. Their power does not lie only in destruction, brightness, or danger. It lies in what they reveal about hidden engines. A jet or outflow is the visible extension of physics operating close to an event horizon. It carries information about spin, magnetic fields, plasma, and feeding. it also carries energy into the galaxy, making the black hole's presence felt far beyond the region where gravity alone dominates. In TON 618, the scale of the central black hole suggests that the engine has lived through extraordinary conditions, perhaps long episodes of feeding and the mergers of earlier giants. Its light reaching Earth is the afterimage of that history. The quasar may no longer exist in the same state now, because the signal is ancient. The galaxy that hosted it has had billions of years to evolve, exhaust gas, merge, fade, or awaken again. What arrives is not a live portrait in ordinary time, but a preserved chapter from deep history. That chapter tells of a universe capable of building engines so large that they challenge measurement and so bright that their light crosses nearly all of cosmic time. At the edge of scale, TON 618 does not close the story. It widens it. It shows that black holes can grow into forms that rival the largest structures of thought, that quasar light can turn the early universe into a readable archive, and that the most powerful beams are not isolated wonders. They are symptoms of a deeper pattern matter falls, gravity deepens, magnetic fields organize, and energy escapes along paths carved through darkness. Not every powerful beam is born from a long-fed black hole at the centre of a galaxy. Some are born in a moment of collapse, when a massive star reaches the end of its life and its core falls inward faster than its outer layers can understand. These beams are gamma-ray bursts, among the shortest and most intense signals known in astronomy. They do not glow for millions of years like quasars. They do not carve radio lobes across galaxy clusters over deep time. Instead, they appear as sudden flashes of gamma rays, the most energetic form of light, arriving from random directions in the sky and fading almost as quickly as they came. For decades, their origin was mysterious. They were too brief, too bright, and too scattered to fit easily into older categories of cosmic violence. Gradually, astronomers learned that many gamma-ray bursts come from distant galaxies, and that their apparent power can exceed almost anything else in the observable universe. The key is focus. The energy is not released equally in every direction. It is concentrated into jets. If one of those jets points toward Earth, telescopes see a burst that can cross billions of light-years and still strike detectors with unmistakable force. The longest gamma-ray bursts are linked to the deaths of very massive stars. Near the end, the star has built a heavy core, layered with the products of fusion. When support fails, the core collapses. A black hole may form at the centre, surrounded by a disk of infalling stellar material. In the chaos of that collapse, magnetic fields and rotation can drive narrow jets along the star's poles. But the jet is not immediately free. It must fight its way through the body of the dying star. For a time, it is buried, drilling outward through dense layers of gas. If it stalls, no bright gamma-ray burst escapes. If it succeeds, it breaks through the stellar surface and releases a focused flash of high-energy radiation into space. The star then explodes as an unusually energetic supernova, while the jet races ahead, carrying the signature of the central collapse. The star dies in all directions, but the most extreme signal leaves through two narrow channels. This makes gamma-ray bursts both powerful and selective. Many may occur without being aimed at Earth, and therefore remain unseen as full bursts. Their jets pass elsewhere, lighting other directions in the universe. The ones detected are the rare alignments. This also means the true event is less impossibly energetic than it first appears if the flash is assumed to spread in all directions. Even so, the focused beam is extraordinary. During its brief life, it can outshine its host galaxy. It can release a flood of gamma rays, X-rays, and later visible and radio afterglow as the jet slams into surrounding material. The afterglow is important because it gives astronomers time to locate the event, study its host galaxy, measure its distance, and understand the environment around the burst. The first flash may last seconds, but its fading echo can continue for days, weeks, or longer. The beam writes a short message, then leaves a trail that can be read. There is another kind of gamma-ray burst, shorter and born from a different catastrophe. When two neutron stars spiral together, they lose energy through gravitational waves and finally merge. Neutron stars are the collapsed cores of massive stars, packed so densely that ordinary matter has been crushed into extreme states. In the final moments before merger, they orbit each other at tremendous speed. When they collide, the result can form a black hole or a heavier compact remnant, surrounded by a small disk of debris. From that central engine, jets may launch. These short gamma-ray bursts are usually briefer than the bursts from collapsing massive stars, but they carry their own importance. They are linked to kilonovae, explosions that can forge heavy elements such as gold and platinum through rapid neutron capture. In this way, one of the universe's fiercest beams can mark the birth of rare elements later scattered into space. A short burst is not only an ending, it is part of the chemical history that eventually enriches planets, oceans, and living worlds. The connection between gamma-ray bursts and gravitational waves has made these events especially revealing. Light and space-time can now carry news of the same catastrophe. A neutron star merger sends ripples outward through the fabric of space-time, while its jets and glowing debris release electromagnetic radiation. Together, they allow astronomers to study the event from more than one messenger. The beam becomes part of a larger cosmic report. It reveals the angle of the outflow, the speed of the ejector, the material around the merger, and the process by which compact remnants form. The strongest flashes are therefore not only spectacles, they are laboratories for matter under impossible pressure, gravity at its limit, and the origin of heavy elements. The universe uses brief violence to make enduring substance. Gamma-ray bursts also reveal how dangerous direction can be. A supernova spreads energy broadly, and distance weakens its effect. A gamma-ray burst, by contrast, concentrates much of its immediate radiation into a narrow path. From far away, it is only an astronomical signal. From too close and directly aligned, it would be a planetary hazard. The atmosphere of a living world provides some protection, but intense gamma rays and high-energy particles can alter atmospheric chemistry. They can damage ozone, changing how much ultraviolet light reaches the surface. They can affect upper atmospheric molecules and possibly disturb climate in complex ways. Such scenarios are studied carefully, but they are surrounded by uncertainty because real planetary outcomes depend on distance, beam angle, atmosphere, magnetic fields, and biology. What is clear is that a nearby directly aimed burst would be among the more severe cosmic threats. What is also clear is that such alignments are rare. Space is vast, jets are narrow, and the most dangerous events are not common in the immediate neighbourhood of the Sun. The danger lies not in everyday expectation, but in what focused energy can mean when geometry is unlucky. The physics of a gamma-ray burst is still difficult because it unfolds under extreme conditions that cannot be reproduced fully on Earth. The jet is likely made of plasma moving at ultra-relativistic speeds, with internal shocks, magnetic turbulence, and radiation processes that transform hidden energy into observed gamma rays. Sometimes the jet may be dominated by magnetic fields, sometimes by matter. Sometimes the observed light may come from collisions within uneven shells of material, while later afterglow comes from the jet striking gas beyond the star. The details remain debated, but the broad structure is strong. Collapse or merger creates a compact central engine. Rotation and magnetic fields help launch a jet. The jet accelerates outward. If it points toward Earth, its radiation is amplified by relativistic motion. A cosmic catastrophe becomes a beam. The briefness does not make it small. It makes it concentrated in time as well as direction. Compared with quasars, gamma-ray bursts are like lightning beside a lighthouse. The quasar endures, fed by a galactic reservoir. The burst erupts, fed by a dying star or merging remnants. The quasar shapes galaxies across millions of years. The burst announces a compact catastrophe across seconds. Yet both depend on the same deeper themes: gravity, rotation, magnetic fields, plasma, and escape through a narrow axis. Both show that some of nature's greatest energies are not spherical. They are collimated, formed into beams by the geometry of collapse. In the great dark, the strongest light often travels not as a glow, but as a spear. This is why gamma-ray bursts occupy a special place among cosmic beams. They are not the largest structures, and they are not the longest lived, but they may be the most intense moments of directed radiation the universe produces. They are sudden doors into the final states of stars and the collisions of compact remnants. They reveal black holes at birth, neutron stars at death, and heavy elements in formation. They show that a star can spend millions of years shining steadily, then end by creating a signal visible across nearly all observable space. In that final act, the star's core collapses, a jet escapes, and for a few moments the universe becomes aware of a death so focused that it can be seen from almost everywhere the beam is allowed to go. A cosmic beam becomes most unsettling when it is no longer only a distant spectacle, but something that can cross the path of a world. Space offers protection through distance. Most violent events are too far away to matter beyond astronomy. A quasar can blaze with the power of 1,000 galaxies and still arrive at Earth as a faint point, because the universe between is vast. A gamma-ray burst can release a narrow flash of extreme radiation, and still be harmless if it erupts in a remote galaxy or points elsewhere. But beams change the meaning of danger because they concentrate energy. They do not need to fill space evenly. They only need alignment, closeness, and time. A planet under such a beam would not experience the event as ordinary heat alone. The first effects would arrive as high-energy photons and particles interacting with the upper atmosphere, changing chemistry before anything on the surface understood the source. In that sense, the danger of cosmic beams is often indirect. The beam may strike the atmosphere, and the atmosphere becomes the battlefield. Earth is not unprotected. Its air absorbs much of the harsh radiation that would otherwise reach the ground. Its magnetic field deflects many charged particles from the sun and from space. The ozone layer blocks much of the sun's ultraviolet radiation, preserving conditions that surface life can tolerate. These protections are powerful, but not infinite. Intense high-energy radiation from a nearby astrophysical event can break molecules apart in the upper atmosphere. Nitrogen and oxygen can be driven into reactive forms that disturb the chemical cycles maintaining ozone. If enough ozone is lost, more ultraviolet light from the sun reaches the surface. The original beam may last seconds, days, or years depending on the source, but the atmospheric consequences can continue long after the first flash fades. A world is harmed not only by what arrives directly from space, but by what that arrival does to its own shield. Supernovae offer one version of this threat. They are not narrow beams in the same way as gamma-ray bursts or quasar jets, but their expanding shock waves and cosmic rays can influence planets over long periods if the explosion is close enough. The first visible light may be beautiful, a new star brightening in the sky. But later, high-energy particles can continue arriving for thousands of years. These cosmic rays may alter atmospheric chemistry, increase radiation exposure at high altitudes, and affect climate in ways that remain difficult to model precisely. Geological evidence suggests that nearby supernovae have occurred in Earth's recent deep past, leaving traces such as radioactive iron in ocean sediments. These events were not close enough to erase life, but they show that Earth does not drift through a perfectly isolated environment. The solar system moves through a galaxy where massive stars live, die, and sometimes leave chemical fingerprints behind. A gamma-ray burst is sharper. Its danger depends strongly on direction. A burst thousands of light-years away might matter if its beam is aimed directly at Earth, while the same event aimed elsewhere would pass unnoticed except perhaps by distant observers in another direction. The atmosphere would absorb the gamma rays high above the surface, but that absorption could produce chemical changes. Ozone depletion is the central concern, because the loss of ozone changes the radiation environment under ordinary sunlight. Surface ecosystems, especially those relying on organisms near the ocean surface, could be vulnerable if ultraviolet exposure increased strongly. The details depend on the energy of the burst, the distance, the width of the beam, the state of the atmosphere, and the resilience of the biosphere at the time. This is why careful language matters. A nearby directed burst would be serious, but real events are rare, and the Milky Way today does not appear to place Earth under an obvious immediate threat from a known gamma-ray burst progenitor. Cosmic danger is not the same as daily danger. It belongs to deep time. Quasar jets operate on a different scale again. Their beams can extend across galaxies and beyond. But the most powerful quasars are very far away. None sits close enough to threaten Earth directly. If a quasar like those in the young universe were active nearby and aimed through a planetary system, the consequences would be extreme. But this is not the present condition of the Milky Way. The black hole at the galactic centre is faint. Sagittarius. A star is not currently producing a quasar jet. Earth orbits far from the centre, in a relatively calm region of the galactic disk. The danger from active galactic nuclei is therefore mostly a way of understanding cosmic possibility, not a practical forecast. It reveals what beams can do when scaled up, not what they're about to do here. The same universe that contains terrifying engines also contains distance, rarity, and geometry, and those three are quiet forms of protection. Still, beams that strike worlds teach an important lesson about habitability. A planet is not safe simply because it orbits within a star's temperate zone. It also belongs to a galactic environment. Nearby massive stars, dense stellar clusters, supernova rates, black hole activity, and gamma-ray burst likelihood all help shape long-term conditions. A world near the crowded centre of a galaxy may face more frequent gravitational disturbances and high-energy events. A world in a quiet outer region may be more protected, though perhaps also formed from material with different chemical histories. Habitability is therefore layered. There is the local star, there is the planetary atmosphere, there is the magnetic field, there is the wider galactic neighbourhood. Cosmic beams remind astronomy that life, if it appears elsewhere, does so inside a universe that can be calm for millions of years and then suddenly disturbed by events far beyond the planet itself. This does not make life fragile in a simple way. Earth's history shows resilience. Life has endured asteroid impacts, climate shifts, volcanic episodes, changing atmospheres, and nearby stellar activity. The biosphere is not a delicate glass structure that shatters at every disturbance, but complex surface ecosystems can be sensitive to radiation, chemistry, and climate. A beam does not need to destroy a planet to change its evolutionary path. It may stress food webs, alter mutation rates, damage shallow marine life, or push climate systems toward different states. Over deep time, such pressures could influence which species survive and which disappear. A cosmic beam may be brief in astronomical terms, yet its biological consequences can ripple through generations. The universe does not guide evolution gently. Sometimes it nudges through sunlight and seasons. Sometimes it intervenes through rare violence. There is also a difference between fear and perspective. The strongest beams sound overwhelming because their numbers are enormous and their physics is harsh. But the sky above Earth is not filled with imminent beams waiting to strike. Most gamma-ray bursts happen far away. Most quasar jets belong to distant galaxies or ancient cosmic epochs. Nearby supernova candidates are watched, but none known appears positioned to threaten Earth with immediate catastrophe. The ordinary hazards of a planet are much closer and more constant than the rarest cosmic extremes. Yet studying these beams matters because they reveal the full range of environments the universe can create. They help explain why some galaxies stop forming stars, why intergalactic gas stays hot, why distant objects flare, and how planets may experience their wider cosmic neighborhood. The same physics that threatens, in rare cases, also helps structure the universe that eventually produces planets at all. Heavy elements forged in stars and spread by explosions become the ingredients of rocky worlds. Black hole feedback helps regulate galaxies. Neutron star mergers create rare elements. Cosmic violence is woven into cosmic fertility. When beams strike worlds, the story is not only about danger, it is about connection. A planet's atmosphere can register events born thousands of light years away. Ocean sediments can preserve atoms made in stellar explosions. The chemistry of air can respond to radiation from a dying star. Life can evolve under skies shaped not only by a parent star, but by the history of the galaxy around it. These strongest beams are reminders that no world is entirely alone. Each planet is embedded in fields, winds, radiation, dust, and ancient light. Most of the time, this connection is quiet. Sometimes, across deep time, it becomes forceful. A beam that begins near a collapsing star or feeding black hole may cross the dark for ages before meeting a world, and in that meeting, the distance between cosmic physics and planetary life briefly disappears. At the centre of the Milky Way, the monster is quiet. It does not dominate the night sky. It does not blaze as a quasar or send a bright relativistic jet through the galaxy. It sits behind thick curtains of gas and dust in the direction of Sagittarius, hidden from ordinary sight, marked mostly by radio emission and by the motion of stars that orbit something dark, compact and massive. This object, Sagittarius A star, contains millions of times the mass of the Sun. Compared with the ultramassive black holes that power the brightest quasars, it is modest. Compared with anything in the solar system, it is overwhelming. Its event horizon is small on the scale of the galaxy, but its gravity governs the innermost stellar orbits of the galactic core. Stars sweep around it in long ellipses, some passing close enough to accelerate to extraordinary speeds before swinging away again. Their paths reveal the invisible centre more clearly than any direct glow could. Something massive is there. Something dark holds them. The quietness of Sagittarius. A star is therefore not absence. It is a state. A black hole can only shine through what surrounds it, and the Milky Way's central black hole is currently underfed. Gas exists nearby, but not in the dense, steady torrents needed to power a quasar. Stars crowd the central region, dust clouds drift, magnetic fields twist, and small flares appear from time to time, yet the engine idles. The accretion flow is thin and inefficient compared with the bright disks of active galaxies. Radiation rises weakly. No great beam crosses the Milky Way from pole to pole. From outside, the galaxy would not be recognized as a quasar host. It would look like a spiral galaxy with a dim central black hole, one of many quiet giants in the present-day universe. But quiet does not mean permanent. Galactic centers change as fuel arrives, as clouds fall inward, as stars are disrupted, and as mergers rearrange the flow of matter. The sleeping monster nearby has likely awakened before. One of the strongest clues lies not in the center itself, but above and below the Milky Way's disk. Giant bubbles of high-energy emission extend on both sides of the galactic plane, forming enormous lobes traced in gamma rays and other wavelengths. They are not beams like the narrow jets of the greatest quasars, but they may be relics of a past outburst from the galactic center, perhaps produced when Sagittarius A star accreted more material, or when intense star formation drove powerful winds. Their scale is immense compared with the quiet source seen today. They rise tens of thousands of light-years into the halo, as if the central region once exhaled with far greater strength. The exact origin remains studied, but the implication is clear: the Milky Way's core has not always been as calm as it appears now. The galaxy carries scars of former activity. A present silence can sit on top of an ancient roar. To understand this, it helps to imagine the galactic center as a place of crowded orbits and unstable supplies. The central region contains stars packed far more densely than near the Sun. Massive stars live and die there. Stellar remnants accumulate. Gas clouds move under the combined influence of gravity, turbulence, and magnetic fields. A cold molecular ring and streams of gas circle the center, sometimes feeding inward, sometimes remaining stalled in orbit. A single cloud passing too close could be stretched, heated, and partly swallowed. A star on an unlucky orbit could be tidally disrupted, turned into a stream of gas feeding the black hole for a time. These events may not create a quasar, but they can brighten the nucleus, launch outflows, and leave lingering effects in surrounding plasma. The difference between quiet and active may be a matter of supply rather than identity. Sagittarius A star has the same essential nature as the black holes inside quasars. It simply lacks their feast. The Event Horizon Telescope made this quiet monster visible in a new way. By linking radio observatories across Earth, astronomers created a planet-sized virtual telescope capable of resolving the region close to the event horizon. The resulting image of Sagittarius A star showed a ring-like glow around a dark central shadow, shaped by hot plasma and the bending of light in strong gravity. The image was difficult because the source changes quickly compared with M87's larger black hole. Sagittarius, a star is smaller, so material near it orbits on shorter timescales, making the view flicker during observation. Yet the image confirmed the same broad pattern seen in M87, a compact dark object surrounded by bright emission, matching expectations for a black hole under general relativity. It was not a quasar image, it was not a jet portrait. It was something quieter and perhaps more intimate, the face of the galaxy's central darkness, not in eruption, but in restraint. This restraint is part of what makes the Milky Way habitable in its current form. Earth lies far from the galactic center, in a region where the black hole's direct influence is negligible. The solar system orbits within the disk, shaped far more by the Sun, local stars, spiral structure, and passing clouds than by Sagittarius A star. If the Milky Way's core became dramatically active, distance would still matter. A quasar-level event at the center would not turn the sky into immediate fire at Earth's orbit, but it could alter the radiation environment of the galaxy, especially along the poles, and contribute to high-energy backgrounds. The greatest danger from active galactic nuclei comes not from gravity reaching across the disk, but from radiation and beams escaping the central engine. Geometry would matter. A narrow jet aimed away from the disk might spare most stars. A wide outflow could heat halo gas. A strong central flare could leave traces in surrounding material. The galaxy's structure would shape the consequences. The sleeping monster is nearby in galactic terms, but still distant enough that its current faintness is part of Earth's long calm. The future will not keep the Milky Way unchanged. The galaxy is on a slow path toward interaction with Andromeda, a neighbouring spiral galaxy moving under mutual gravity. Over billions of years, the two galaxies are expected to merge, their stars mostly passing between one another because space is so empty, while their gas clouds collide, compress, and fall into new patterns. Such a merger can drive gas toward galactic centres. It can awaken black holes. The central black holes of the Milky Way and Andromeda may eventually sink toward one another and merge, releasing gravitational waves and forming a larger remnant. During the long disturbance, fresh material may feed the central engine, perhaps creating an active phase far brighter than the one seen today. This is not a near-future event on human scales. It belongs to deep cosmic time, but it shows that quiet galaxies are not final products. They are temporary arrangements. The same galaxy that now hosts a faint central black hole may one day pass through a phase of renewed fire. The Milky Way's past and future place, Earth's galaxy inside the larger story of cosmic beams. It is not separate from the quasar universe. It is a quieter chapter of the same book. The black hole at its heart is a dark engine without much fuel. The bubbles above and below the disk may be old breath from earlier activity. The coming merger with Andromeda may bring new disturbance and perhaps renewed feeding. The pattern repeats across cosmic history. Galaxies assemble. Gas flows inward. Black holes awaken. Beams and winds push outward. Fuel dwindles, and the engines sleep again. A galaxy can be active, quiet, and active again, each phase leaving marks on stars, gas, and halo. Sagittarius, a star, is therefore not only an object. It is a reminder that the most extreme physics in the universe is not confined to remote quasars. The machinery is present in the local cosmic home, subdued but real. This gives the Milky Way a strange dual character. It is familiar. The broad band of stars across dark skies, the galaxy that formed the Sun and Earth. It is also a structure built around a hidden central abyss, surrounded by relics of past violence and possibilities of future awakening. The quiet centre does not cancel the violence. It contains it in pause. In that pause, stars continue their orbits, gas drifts through dust, and the black hole waits without intention, responding only to gravity and supply. If enough matter falls inward, the engine will brighten. If magnetic fields organize strongly enough, outflows may rise. If the future merger delivers fuel, the sleeping monster may speak again. For now, the strongest beams remain elsewhere, crossing distant galaxies and ancient epochs. But at the heart of the Milky Way, the same laws are already assembled, silent in the dark. The universe does not end its violence when a quasar fades. It stores the conditions for future fire inside the slow motions of galaxies, the drift of gas, the fall of satellites, and the long gravitational pull between neighbouring systems. A galaxy may look settled for billions of years, its spiral arms turning quietly, its central black hole dim, its stars aging in place. Yet on deep timescales, stillness is only a temporary arrangement. galaxies move through groups and clusters. They pass near one another. They tug at one another's disks. They strip gas, stretch tidal tails, and sometimes merge into larger forms. Each encounter can disturb material that once orbited calmly. Gas loses its neat rotation. Clouds collide. Dust lanes twist. Matter that had remained far from the centre can begin a slow inward journey. At the heart of the galaxy, the black hole waits, not with desire, but with gravity. It becomes powerful only when the galaxy delivers fuel. The future of cosmic fire is therefore written in galactic motion. The strongest beams do not need to burn forever, because the universe can awaken them again. In the early universe, awakenings are common. Galaxies are smaller, closer, and richer in cold gas. Mergers happen often. Black holes grow rapidly. Quasars flare across cosmic history like cities lighting up in a younger night. Over time, the universe expands. Galaxies become more widely separated. Gas is used up, heated, or locked into stars. Major mergers become less frequent. Many black holes fall quiet. This decline does not mean the engines have vanished. It means the conditions have changed. The darkness remains at the centers of galaxies, surrounded by stars, remnants, and occasional drifting clouds. A quiet black hole can wait for immense spans without changing its basic nature. Then a disturbance can begin again. A small galaxy falls into a larger one. A bar forms across a spiral disk and channels gas inward. A molecular cloud loses angular momentum and approaches the core. A star wanders too close and is torn apart. Each event may feed the black hole briefly or steadily, creating flares, winds, or renewed jets. The future is not a simple dimming. It is a pattern of fading and rekindling. The coming merger between the Milky Way and Andromeda is one example, though it belongs to a future far beyond human history. The two galaxies approach each other under gravity, each carrying hundreds of billions of stars and vast halos of dark matter. Their stars are so widely spaced that direct stellar collisions will be rare, but their gas clouds will not pass so quietly. Gas can collide, compress, and fall into new orbits. Star formation may surge in some regions. Dust and gas may be driven toward the growing central remnant. The black holes at the centers of the two galaxies may eventually sink inward through gravitational interactions with surrounding stars and gas after a long dance. They may form a binary, spiral closer, and merge. That merger would release gravitational waves, ripples in space-time carrying energy away from the system. The remnant black hole would be heavier, perhaps spinning in a new direction, surrounded by a galaxy no longer shaped like the Milky Way or Andromeda, but transformed into something larger and older. If enough gas reaches the center during this process, the quiet monster may brighten. It may not become one of the greatest quasars in the universe, but it could enter an active phase far stronger than today's faint glow. The future beam, if one forms, would depend on alignment, spin, magnetic fields, and fuel. A merger does not guarantee a jet. It sets the stage. The black hole must receive material in a disk. The disk must become ionized and magnetized. The geometry must allow energy to escape along poles. If those conditions align, a new outflow may rise from a galaxy that once seemed settled. The beam could push into the remnant's halo, heat gas, and carve cavities. It could mark a renewed conversation between the central black hole and the galaxy around it. This is how cosmic evolution often works. Large structures grow through collisions, and collisions feed central engines, and central engines push back against growth. The universe builds and restrains itself through the same events. Fire is not separate from architecture. It is one of the tools by which architecture changes. Far beyond the local group, galaxy clusters preserve even larger versions of this cycle. In the centers of some clusters, enormous elliptical galaxies host supermassive black holes that erupt repeatedly. X-ray observations reveal cavities in the hot cluster gas, bubbles inflated by jets. Radio maps show older lobes detached from current activity, ghostly traces of previous outbursts. The black hole turns on, launches jets, heats the surrounding gas, and reduces the rate at which gas cools toward the center. Then, as the activity weakens, cooling may resume, feeding the black hole again and triggering another outburst. This feedback loop can continue across vast spans. It is not a smooth engine with perfect rhythm, but a long, uneven breathing. Inhalation is fuel falling inward, exhalation is energy driven outward. The beam becomes one phase of a cluster's metabolism. Without it, the central galaxy might grow differently. The cluster gas might cool more rapidly, and star formation might proceed in ways the universe often prevents. The strongest beams therefore help maintain the large-scale texture of cosmic structures. They are not rare decorations. They are part of the system's self-regulation. In the far future, the nature of cosmic fire changes as fuel becomes scarcer. Stars will continue forming for a long time, but the rate declines as gas supplies are exhausted or locked away. Massive stars, the ancestors of supernovae and long gamma-ray bursts, become less common as star formation slows. Quasars become rarer because fewer galaxies contain the cold gas needed to feed supermassive black holes at high rates. Yet black holes themselves remain. They are among the longest-lasting objects in the universe. Stellar remnants accumulate. Galaxies settle into older forms. Encounters still happen, especially inside bound groups and clusters, where gravity holds systems together despite cosmic expansion. Occasional mergers may still deliver fuel. Tidal disruptions may still occur when stars wander near central black holes. Compact objects may still collide, producing gravitational waves and sometimes short bursts if matter is present. The universe grows quieter, but it does not become silent all at once. Its strongest lights become rarer, more isolated, and more dependent on chance encounters. A future observer in a much older galaxy might see fewer quasars in the sky, not because the laws of physics have softened, but because the ingredients for great engines have become harder to gather. There is a melancholy grandeur in this. The most powerful beams are temporary even when they last millions of years. They belong to eras of abundance, disturbance, and growth. A quasar is the sign of a black hole in a moment of opportunity. A gamma-ray burst is the sign of a massive star at the instant of collapse. A radio jet is the sign of magnetic order imposed on falling plasma. None is eternal, yet their effects can outlive them. A jet can leave radio lobes that fade slowly. A burst can enrich space through the explosion that surrounds it. A quasar can change the gas supply of a galaxy, shaping star formation long after the central light dims. The beam passes, but the universe remembers through structure, cavities, bubbles, heated halos, chemical enrichment, and altered galaxies all become records of fire that is no longer burning. Deep time is full of such after-images. The future of cosmic fire also points back to the beginning. The same principles repeat across scale and era. Gravity gathers matter. Rotation prevents simple collapse. Magnetic fields organize plasma. Radiation pushes back. Outflows reshape the environment. Whether in the young universe around a growing quasar, in a galaxy cluster breathing through repeated jet activity, or in a future merger remnant awakening after long quiet. The pattern remains. The strongest beams arise when collapse does not end in disappearance alone, but in escape along a narrow path. They are moments when the universe turns inward motion outward. They show that even as matter falls toward horizons, some energy is redirected into space, crossing distances that the original fuel could never have travelled on its own. The future does not promise endless brightness. It promises transformation. Some galaxies will fade, some black holes will sleep, some will wake when disturbed. New beams will rise, old lobes will fade, and the cosmic web will carry traces of both. In the largest view, the universe becomes a long sequence of awakenings and rests. Fire emerges, shapes its surroundings, and subsides. Darkness gathers, waits, and sometimes becomes an engine again. The most powerful beams are therefore not only relics of a violent past, they are possibilities held in the structure of galaxies, waiting for gravity to rearrange the night. The strongest light in the universe often begins where light should disappear. This is the quiet contradiction at the heart of cosmic beams. A black hole forms a boundary beyond which no signal returns, yet the environment around it can become brighter than a galaxy. A dying star collapses into darkness, yet in its last moments it may launch a flash visible across billions of light years. A neutron-star merger crushes matter into extreme states, yet it can send out radiation, gravitational waves, and newly forged elements, again and again. The universe shows that collapse is not only an ending, it is also a way of concentrating energy until some of that energy finds a path outward. The beam is that path made visible. It is not random brightness, but direction. It reveals that nature can take chaos, pressure, rotation, and magnetism, then organize them into a narrow escape route through the dark. In this sense, the most powerful beams are not separate curiosities. They are expressions of a deep cosmic pattern. Matter gathers under gravity. The gathering becomes too intense to remain simple. Rotation builds disks. Magnetic fields strengthen. Radiation pushes back. Some material falls beyond recovery, while some energy is carried away at nearly the speed of light. The result may be a quasar jet spanning intergalactic space, a blazar aimed across the line of sight, or a gamma ray burst marking the death of a massive star. Each form differs in duration and scale, but each tells the same underlying story. The universe is shaped by the contest between inward collapse and outward release. This contest is written into galaxies. Supermassive black holes do not merely sit in their centers as silent weights. When fed, they influence the gas from which stars form. Their jets heat cluster atmospheres, inflate bubbles, carve cavities, and slow, cooling flows. Their radiation and winds can clear central regions or disturb them into new patterns. A beam crossing a galaxy is not only a display of force, it is part of galactic memory, part of the record of how stars, gas, and black holes regulate one another across deep time. Creation and destruction become difficult to separate. The same outflow that suppresses star formation in one region may compress gas in another. The same explosion that threatens life from too close also scatters elements needed for planets. The same merger that releases a deadly flash can help make heavy atoms later folded into worlds. Cosmic beams therefore resist simple judgment. They are not good or evil, not merely beautiful or terrible. They are processes by which the universe changes its own conditions. Their meaning also lies in what they allow astronomy to know. Quasars illuminate the early universe like lamps behind a fog, letting distant gas reveal itself through absorbed light. Jets show magnetic fields and plasma physics operating on scales no laboratory can reproduce. Gamma-ray bursts point to black holes being born, neutron stars colliding, and matter behaving at densities far beyond ordinary experience. Even the absence of a beam can be informative, showing a black hole without sufficient fuel or a galaxy in a quieter phase. The cosmos speaks through brightness, but also through silence. Sagittarius. A star is quiet now, and that quietness says something about the present state of the Milky Way. Ton 618 blazes across ancient distance, and that brightness says something about the early growth of giants. M87 sends a jet through its host galaxy, and that beam links the edge of an event horizon to structures thousands of light years away. Each object becomes a chapter in a larger investigation. The more powerful the beam, the more carefully it must be understood, because power alone can mislead. Perspective can amplify a blazar. Distance can hide a host galaxy. Dust can obscure a nucleus. A short flash can represent a narrow jet rather than a spherical explosion. Astronomy learns humility from these beams. It learns that the universe's appearance depends on angle, wavelength, time, and the limits of measurement. What first looks like a star may be a quasar. What first looks like empty static may be the galactic center. What first seems impossible may become ordinary once the right physical engine is found. Yet even when explanations improve, mystery does not vanish. It moves deeper. The questions become sharper. How did the earliest supermassive black holes grow so quickly? How exactly do magnetic fields extract rotational energy near spinning horizons? Why do some active nuclei launch powerful jets while others remain radio quiet? How do gamma-ray burst jets form, accelerate, and break free? How often have cosmic beams influenced planetary environments across the history of the galaxy? These are not gaps of ignorance in a simple story. They are active edges, places where observation, simulation, and theory continue to meet. The strongest beams remind science that the universe is understandable, but not exhausted. Known laws can explain much, yet the most extreme cases keep pressing against the boundaries of those explanations. There is calm in that uncertainty. The universe does not need to be fully settled to be meaningful. Its unresolved parts are not failures of wonder, but sources of it. A beam crossing millions of light years is a physical event, governed by fields, particles, and space-time. It is also a sign that scale can connect the smallest and largest realms. Near an event horizon, particles move through a region that may be smaller than a planetary system. Far away, their energy heats gas across a cluster of galaxies. A collapse lasting seconds can be seen across cosmic history. A black hole smaller than its host by an almost absurd margin can shape the fate of that host's stars. The universe is full of such connections, where small centers influence vast surroundings, where brief moments leave long traces, and where darkness becomes the source of light. In the end, the most powerful beams reveal a cosmos that is neither peaceful nor meaningless. It is restless, structured, and profoundly connected. It builds stars from gas, destroys stars into remnants, feeds remnants into black holes, and lets black holes push energy back into the galaxies that feed them. It forms worlds from the ashes of earlier violence and shelters them for long, quiet intervals between rare disruptions. It sends ancient light across expanding space, allowing distant engines to be studied long after their original fires may have changed or faded. Nothing in this story stands alone. The beam, the black hole, the galaxy, the gas, the planet, and the observer all belong to the same unfolding system. The terror of these beams lies in their intensity. The wonder lies in their role. They are not merely signs of destruction, but signs of transformation. They show how the universe moves energy from hidden depths into open space, how it regulates its own growth, and how even the darkest regions can leave luminous marks across time. Somewhere, a massive star is nearing collapse. Somewhere, two compact remnants spiral closer. Somewhere, a quiet black hole receives a new stream of gas. Somewhere, magnetic fields tighten around a disk and a narrow path begins to form. Most of these events are far away, and many will never point toward Earth. Some will be missed. Some will be detected as brief flashes, faint radio lobes, shifting spectra, or distant points of impossible brightness. Together they form the continuing language of cosmic power. The universe does not shout everywhere at once. Often it speaks in beams, thin, ancient, focused lines of energy crossing the dark, carrying news from the places where matter falls deepest and light escapes last. Beyond the beams, the universe settles back into silence. The light fades, the jets thin, and the distant engines return to darkness or wait for new fuel. Yet the traces remain in heated gas, altered galaxies, scattered elements, and ancient photons still crossing space. The strongest beams do not close the cosmic story. They leave it open, widening into questions of growth, collapse, and renewal, somewhere far beyond the Milky Way. An old quasar's light continues its journey through expanding darkness. Somewhere else, a quiet black hole holds its place at the center of a galaxy, surrounded by stars that circle without knowing the force beneath them. The universe keeps its deepest powers hidden until matter falls, fields twist, and a narrow path opens outward. Then, for a moment or for millions of years, darkness speaks in light. The beam crosses the void, not with intention, but with consequence. It carries the memory of collapse into the wider cosmos. And then it too becomes part of the background, fading into distance, softened by time. What remains is the pattern stars are born. Stars die. Black holes sleep. Black holes wake. Galaxies breathe slowly through fire and quiet. The most powerful light is never separate from the dark. It rises from it, circles it, escapes beside it, and reveals it. In that balance, the universe appears less like a finished machine and more like a long unfolding tide, vast and patient, violent and calm. Its brightest lines pass through the night and vanish, but the mystery they leave behind continues to glow.